Okay, it's a great pleasure to have Tom Faulkner here today to tell us about the holographic map as a conditional expectation.
Okay, well, thank you very much for inviting me. So I'm going to tell you about this paper. Just interrupt me if something goes wrong with or if I'm not clear on something. Um, okay, so I'm going to tell you about this paper um, that I put out recently, and there's a few takeaways that I'll summarize now. There's some concrete things which are kind of simple. They're sort of simple observation. That the first observation is that the quantum error correcting codes that have been put forward, or some of them at least, as a model of ADS CFT, naturally give rise to this mathematical structure called a conditional expectation. And this is a well-studied mathematical structure in operator algebras, for example. So that's really just a simple observation starting from well-known results, and that allows you to rederive some of the well-known results very quickly. This observation also strengthens a connection to a paper that came out a year and a half ago, maybe, which I found very confusing and I didn't really know what to make of. This paper by Horacio and Marinia et al., which made some sort of speculative connections between the mathematical structure of superselection sectors in quantum field theory and the holographic map. Yeah. Now, there's some more speculative parts of this, which is basically when I take this observation and I just push it as far as I can. So part of that, well, I'll try to talk a little bit about a picture of entanglement wedge phase transitions, which are sort of an interesting structure that arises in ADS CFT, and I'll try to give some description in this language. This is speculative, and I don't know if this is true. This may not hold up. Essentially, I'm studying something called exact recovery. That's the thing that I'm studying here, and there are well-known shortcomings of exact recovery, and so I'll mention a few of those. Really, the only reason I'm doing that is just because it's just to get started. I just want to do something to get started. It's clear that the next step is to move on to approximate recovery, and so yeah. Okay, so let me start by summarizing some previous results. So this is a model of entanglement wedge reconstruction. I will call it this model complementary recovery. And it really, I guess, started with this ADH paper, but then was formalized by Dong, Harlow, Wall, and then Harlow in particular, and then more recently it was studied in infinite dimensional dimensional setting, in particular using von Neumann algebras and general von Neumann algebras by Kang and Kolchmeyer. So this paper here. And so really, I'm just going to summarize their results and put them in a slightly different language, which will make it a little bit easier to see how the conditional expectation arises. Okay, so the starting point is some physical Hilbert space. This is you should think of as the Hilbert space of the boundary CFD. Okay, so I'll call that kappa. And then we have a code subspace, I'll call H. You should think of this maybe as the bulk gravitational theory, as the Hilbert space, which is described by effective field theory, say in ADS. I'm not being exactly clear on what I'm going to pick for my code subspace. This is pretty standard. It's not really clear how to define it in general, but I think perhaps the spirit of this quantum error correcting approach is that really the details of how you pick it don't really matter. There's something robust about various ways of picking a code subspace, which will give in principle, should give rise to something that looks like gravitational physics. And then there's some isometric embedding between these two Hilbert spaces. So it's an isometric embedding. It satisfies V dagger V is the identity on the code subspace, and VV dagger is a projector, which I'll call E. So E is the code subspace projector. It lives in the physical Hilbert space and projects to the code subspace. Okay, so the question that entanglement reconstruction tries to address is how does this map, this isometric embedding, restrict to local algebras on these two Hilbert spaces? So, so the picture you should have in mind is the following. So this is a picture of ADS CFT, really. So this is ADS CFT. This is really just a time slice, some t is equal to 0 slice. We have some boundary regions, which will have algebras associated to them. So I won't refer to the boundary region, I'll just refer to the algebra. So M is some region on the left here, over here. Different color. M is some region over here on the boundary. And we know that given a region on the boundary of ADS, then it's natural to look for the RT surface. And so here's the RT surface. Here's the RT surface that goes through the bulk of ADS. And then there's this region in between the RT surface and the boundary region, which is sometimes called the homology region. And there's an algebra associated to that. So algebra of operators, and I'll call that N. So there's some association between M and N. But there's also commutant algebras. So I'll define what the commutant is in a little bit, but it's basically the complement. So if I take everything complementary to M on the boundary, that defines M prime, some region, some algebra M prime, which is associated to the complement region. And similarly in the bulk, you have this N prime. Okay, so these are going to be algebras respectively on the physical Hilbert space and on the bulk Hilbert space, and we have to understand how they're related. So that's the question of bulk reconstruction. More specifically, M is a boundary algebra. I really should talk about things in space-time. I'm just drawing a t is equal to 0 slice, but I'm going to take M to be a von Neumann algebra. And you should think of von Neumann algebras as being associated to causally complete regions on the boundary. So causal diamonds, for example. So here's a picture of a causal diamond on the boundary, and it's all the operators that are associated to that causal diamond. If you really want something more precise, then it's field operators appropriately smeared and also made into bounded operators. So this is a subalgebra of all possible operators that you can write down in the quantum field theory, all possible bounded operators, which is B of kappa. And as I said, N is a bulk algebra associated to the entanglement wedge. I'm also going to assume that it's a von Neumann algebra. And so it should also be associated to some causal diamond in the bulk. And N is some subalgebra of operators on the code subspace on H. The commutants are defined as follows. For M, it's just all of the operators in the physical Hilbert space that commute with M. Okay. And similarly for N. Okay, so now developments in the quantum information approach to ADS CFT, in particular, really the Ryu-Takanagi formula was the start of all of this, and then various quantum corrections and an understanding of how relative entropy, where you take two states and you compare them, maps under ADS CFT, allowed us to give a precise characterization of how to relate N and M. And the condition that I'm going to use that derives from this knowledge, I'll call the DHW condition. Okay, so this is a definition. This is the DHW condition. It says the following: given two vectors in the physical Hilbert space, if they're, so I'll give this condition and then I'll try to unpackage it a little bit if you don't know what I'm talking about. If I take the two vectors and I consider their induced states on the commutant algebra in the bulk and they're equal, then that implies, this is the condition, that if I look at them on the boundary after mapping through V using this isometric embedding, and I look at them in the commutant algebra on the boundary, then they're also equal. Okay, so this is a condition, so it's not automatically true. It's just a condition that I'm going to impose on the code on this V, and I'll give it a name. I'm going to say that this implies that n is reconstructible from M, and we'll see in a little bit why the hell I'm using that language. Okay, but okay, so n is reconstructible from M. Okay, so let me unpackage it a little bit. Yes, yeah, go on.
Sorry, can you just quickly remind me why is it the commutant algebra is appearing here?
Yeah, so I'll give you a physical way to think about this in a little bit. So let me make some comments, and if I don't address that, please ask it again. Okay, so firstly, let me sort of define what I mean here. So omega psi is sort of the way that I'm going to refer to as a state induced by a vector. So states are often in the operator algebra language I thought of as positive linear functionals on the operators. If you like, they give the expectation values of all possible operators. You can also think of it as just an algebraic version of a density matrix. So here, omega psi is a global state on B of H, so it's a pure state on the bulk Hilbert space, and it really defines all correlation functions in that state. The restriction just means only feed in operators from the commutant. That's what the restriction means. It's really an algebraic version of the reduced density matrix. So what this statement is saying is the reduced density matrix for the complement region in the bulk, if those two are the same in the bulk, then they should be the same on the boundary. Okay. Okay, so physically, all this is saying is that information about n, which is encoded in the difference. So the two vector states are going to be different in n, but they're the same in n prime. Any information that's in n cannot be recovered from n prime. Okay, so I might act with a unitary on n, the states are going to be different, but in n prime, they're not different. And I can't detect that unitary on n prime, sorry. So it's some version of privacy. It's telling you that anything you do in n can't be detected in n prime. Okay, does that help?
Yeah, I think so.
Yeah. So the other thing about it is that it's often it was derived in DHW by appealing to relative entropy. So it says that if I look at the relative entropy on the commutant in the bulk for two different states, and they're equal, then the relative entropy on the boundary for two different vectors, in M prime should also equal 0. So this is equivalent because if the relative entropy vanishes, that means that the linear functionals are the same. Now, this was used in DHW because it can be derived from the JLMS condition. The JLMS condition is a much stronger condition. It tells you that the relative entropy between any two states in the bulk is equal to the relative entropy between any two states on the boundary. Not the case where they vanish. So it's a much weaker condition than JLMS, but it can be derived from JLMS. The other thing about it is that as a condition, it's assumed that it's been assumed in the past, at least, that it's correct up to non-perturbative errors in G Newton. So it's something that's in principle correct to all orders in G Newton, although in practice that's not really true, and it's now known that this is only true for something called the reconstructible wedge and not for the entanglement wedge. But really, the difference between the reconstructible wedge and the entanglement wedge, there's not very much difference, and for our purposes, I'm going to assume that they're the same. So this assumption is related to this assumption that I'm going to be working with exact reconstruction. So everything will be exact. Yeah. Okay. So that's the condition that I'm imposing that is going to somehow relate n and m. It's actually quite a weak condition. I gave it a name, so n is reconstructible from m. A much stronger condition is something called complementary recovery. So this is not yet complementary recovery. So what is complementary recovery? So I'll give it a name too before I define it. I'll say that n is c reconstructible from m. So that I'll add a little c. So c is very important there. If both n is reconstructible from m and n prime is reconstructible from m prime. Okay, so it's two conditions. It's two conditions on the bulk algebras and on the boundary algebras. And this is a much stronger condition. So one important point that I sort of should mention is that before we impose this complementary recovery condition, if n is recoverable from m, then any subalgebra of n is also recoverable from m. So that sort of tells you that it's a weak condition. Also, if I have two algebras, n1 and n2, that are both recoverable from m, then their union, if I take all the operators generated by both of them, is also recoverable from m. Okay, so all right, so this is the structure that I'm introducing, but really to understand it, I'm going to introduce a well-known theorem. This theorem was proven in the ADS CFT context first by Harlow, then in infinite dimensions by Kang and Koltmeyer, but it actually goes back a long time. There's a paper in the early 80s that study exactly this theorem, and then it goes back even further than that. So this is just well known, but it tells you why I'm calling n reconstructible from m from this DHW condition. So this is the main theorem that we're going to use. The idea is the following. If we have this DHW condition that I was promoting, so this implies this for all states in the code subspace, then there are two equivalent conditions. So the following three conditions are all equivalent to each other. So the first one is essentially a Heisenberg picture version of one. So the second condition, two, is a Heisenberg picture condition version of one. So it's a statement about the operator algebras. So it's basically the following statement. If I take the following quantum channel, so quantum channel is just a map on operator algebras, and I think about the following global quantum channel. So it's going to take operators on the boundary Hilbert space to operators on the bulk Hilbert space, and it's just defined by this isometric embedding. So it's just V dagger conjugating by V. Okay, so the conjugating by V takes an operator on the boundary Hilbert space and puts it in the bulk. If I restrict that global map to M prime, then in principle I could get anything in the bulk, any operator in the bulk. But this DHW condition tells me that I have to get something in N prime. Okay. So if I conjugate by V dagger V on M prime, then I get something in N prime. Okay, so then that's the Heisenberg picture version of one. And then the final condition that's equivalent to this is the following reconstruction map. So I'll give it that name and I'll explain why it's a reconstruction map. So there exists another quantum channel, which again is a map on operator algebras, but now between N and M without any primes. This map is a special kind of map. It's called the star homomorphism, which means that it preserves the algebra. So if I have a product of N1 and N2, Then if I apply beta to it, I get beta of n1 times beta of n2. And it has the following properties. If I take beta of n and I apply it on v, then I get v times n. Okay, so let me again try to unpackage all of this. So this correspondence between alpha prime, so I didn't really define what alpha prime was. Alpha prime is this restriction of this global map to m prime. So that's what I'm going to call alpha prime. So this correspondence between this alpha prime map, which is a map between m prime and n prime, and this beta map, which is a map between n and m, is something called a dual map. It's really, for those who have been following the recent literature, it's a version of the PETS map. It's a funny version of the PETS map without the modular conjugation operators, if you know what they are. As I said, these are both quantum channels. When I say quantum channel, I mean something different to what quantum information people mean by a quantum channel. It's really, to me, it's a map on operator algebras. So it's a Heisenberg picture version of a quantum channel. So often when you talk to quantum information people, they'll be talking about maps on density matrices. So it's the it's like the adjoint of that map, and it's the Heisenberg picture version as opposed to the Schrodinger picture version. And the final condition explains this name reconstructible. Beta of n is a representation, so it's an operator on the boundary Hilbert space that is representing the bulk operator n. And it acts on the code subspace, which is here given by v times psi, as it should do, right? It's v times n. So that's this final condition. The box condition here is just telling you that. The box condition is telling you that you have some reconstruction of the bulk operators in terms of boundary operators. And this is usually what we mean by entanglement wedge reconstruction and so forth. Okay. Okay, so a few more comments. So there are all these sort of things that I didn't mention in this theorem, which were bracketed. So there's this alpha prime is faithful. It's just some extra condition that you impose, and beta is unital. So these are just two extra conditions that actually arise if you assume that there exists a vector in the code subspace for which v psi is cyclic and separating for the boundary algebra. That just means that v psi is sufficiently entangled between when I think of it as some state. If I think about the reduced density matrix for M, then that density matrix is full rank. So that's the condition. If you have that, then you get some nicer properties, and those properties I'm going to assume going forward. Okay. So the fact that the final comment is that the fact, that beta is a star homomorphism means that if I apply beta to the bulk algebra n, then that actually defines a von Neumann algebra on the boundary. So n beta is itself a von Neumann algebra just because it preserves the algebra. In particular, it's a von Neumann subalgebra of M, just because of this homomorphism property. Okay, so this is a theorem. It's a way to go from this global map, which restricts to alpha prime, to beta, this reconstruction map. When we have complementary recovery, we can apply this theorem twice because we have this DHW condition twice. Right? So the theorem applies to the DHW condition once, but we can now apply it twice. So in particular, when we apply it twice, I've drawn a picture here. We have 1 and 2 in green and in red. It's not very clear. In green and red. So the first time we applied it, we started with this alpha prime map. Oh, wow. Did I mess up something? This arrow is wrong. Sorry. Yeah, good. Okay, so we started with this alpha prime map, which maps from m prime to n prime in the bulk. And we got out this reconstruction map, which maps from n to m on the left here. But now we apply it again. We use the DHW condition for the commutant algebra, which gives you this map from m to n. And then we get beta prime, which is this reconstruction map on n prime to n prime. Just a comment here is that this, if you like, a language that I probably should use is that complementary recovery is going to be essentially equivalent to an entanglement wedge. So this C recovery condition. If I just had the recovery condition, then as I said before, any subalgebra of n is recoverable from M. Right, so it doesn't define the entanglement wedge. It just defines some subalgebra of the entanglement wedge. You get the complementary condition when you push this right to the as far as you can go, essentially, to the entanglement wedge. Okay. But if you do have this entanglement wedge, if you do have this complementary recovery region, then the claim is that you get this thing called the conditional expectation. So let me explain that. So, so firstly, the idea is we take some of the two of these maps that I've just defined, and we're going to compose them. I'm going to compose the following: beta and then alpha. So what is that doing? If I look on the left here, alpha is firstly taking an operator in M, pushing it into the bulk, and then beta is pulling it back out. Okay, so that's what this map is doing. Notice that I only get this map if I have C reconstructibility, because C reconstructibility. I only get this map because I'm using both the red and the green maps here. Okay. Good, but this map is a map between M, and it does get you back to M, but it really gets you back to this subalgebra in M, so N beta, this thing that I called N beta. So it's a map from M to its subalgebra. The claim is that this map is something called a faithful conditional expectation. A faithful conditional expectation is one of these quantum channels on operator algebras, but it's a quantum channel that takes you from some algebra to a subalgebra with an extra property, which I'm going to define in a little bit. But the important point is that this conditional expectation preserves states in the code subspace. So not only does it exist, but it preserves states in the code subspace. That's this statement. So I'm going to come back to these two things. Let me just tell you what a conditional expectation is. So a conditional expectation, as I said, is a map from an algebra, which I'll just introduce two new algebras, A and B. So B is a subalgebra of A, and a conditional expectation is a map between A and B. That satisfies the following property. If I have B1, B2 in B, and A in A, and it satisfies this equation, E of B2, A, B1, I can just pull out B2 and B1. So in particular, if I just set A equals to 1, E of 1 is 1. That's a property of the conditional expectation. Then E just fixes the subalgebra. So if I apply E to the subalgebra B, it fixes it. It's like the fixed point of that map. Anything else, it does something else to it. But it has the following property. This is called the bimodule property. It's sort of a non-trivial thing. It doesn't always exist, in particular for general von Neumann algebras. So it's a structure that I'm going to use that does sometimes exist for complicated von Neumann algebras, like these type 3 von Neumann algebras, which are appropriate for quantum field theory, but they're not always guaranteed to exist. Now, you should contrast this with a map that goes from the subalgebra to the algebra. So I could easily think of a map that goes from B to A, which is just the inclusion map. I just take B and I include it in A. And that always exists. But this is sort of reversing that map. So E is reversing it. It's called a conditional expectation because it comes from something in commutative algebras, which is just a theory of probability, really, probability theory. So it's a non-commutative version of conditioning on some random variable. So B here would be that random variable. And another way to understand it is just to give two very simple examples that always come up, which is the simplest is just a partial trace. So if I take, if I assume that there's a Hilbert space and a tensor product in that Hilbert space, HA is HB tensor HC, then I have bounded operators on those Hilbert spaces. I have bounded operators on HA, and I have bounded operators on HB, and that's a subalgebra of HA. And I can indeed find a map between those two, which is just by tracing over this C factor. If I take an operator in A and I do a partial trace over C and I normalize it appropriately, then that's a conditional expectation that has the right properties and so forth. Another common one is if my algebra has some symmetry. So for example, so U of G is some operator that implements some symmetry. And if I average over that symmetry, then that is a map from operators in the original operator algebra to the fixed point of that symmetry. So B, in this case, the subalgebra is just the fixed point algebra of U of G. So that is also a conditional expectation. Okay. So back to the claim. So the claim was that E is this conditional expectation, and indeed you can see that by just a direct calculation. If I apply E to this subalgebra, beta of n, this is the subalgebra, then what happens is you can write that E was just beta alpha, so I just have beta alpha beta. It turns out that you can easily show that alpha beta is the identity, and that just follows from this reconstructibility condition. So beta of nv is vn. And you apply that and you get this is the identity, and so this does fix the subalgebra. You can also check that it has this bimodule property as well, quite easily. It fixes the states on the code subspace, just again by a direct calculation. This is a state on the code subspace. I have to apply this isometric embedding, but then I can write this like this, which then I didn't write, but I could write like alpha, beta, alpha, m, like this. And again, alpha, beta is the identity, so I can cancel it off. And then I just get back the original state. So it fixes states on the code subspace. Okay, so maybe I should pause for questions. Any questions? Time. Okay, there's no questions, I'll keep going. All right, so this is just some mathematical structure. It's convenient to introduce because now we can just Google search for conditional expectation, and then we can see all the results that there are, and there's actually quite a lot. So for example, now we understand all these properties like the equality of relative entropy through the code, which is this JLMS condition. That's sort of well known for a long time. You can look at it up in a book by Pets or something. If you have this conditional expectation, then that's sort of trivially true. You also have this equality of bulk and boundary modular flow, which is something that I've exploited a lot in the past. And this is just a well-known consequence of the theorem by Takasaki in the 70s, I think, when you have this conditional expectation. Let me give a schematic picture of what's going on, and this is a misleading picture.
Actually, can I just ask a question,
Yes.
maybe?
Yeah.
So when you realized there was this conditional expectation, this is just something that you weren't adding any additional assumptions to what was
No.
known before. It was just sort of a recognition that the structure that you
Oh yeah,
have
yeah, yeah,
is
yeah, yeah. That's
okay.
right. Yeah, that's right. And Harlow would like to draw these pictures with this sort of code. This was
Yep.
Harlow's code. I'm sure you're aware of it. This is just a picture of a conditional expectation in finite dimensions.
Okay.
You can go through and see that. Yeah.
Okay.
Yeah.
Good.
So it's just giving a name to something that was already there, and maybe that's not so useful. It's just a mathematical thing, whatever. But I think it is somewhat useful because it does let you see all these other results that are out there. I'll give you a flavor of some things that are out there. But this is also new to me, so there's more things that need to be understood or could be exploited, probably. Okay. So let me give the following schematic and probably misleading picture. There's probably a better picture, but this is a picture for some reason that is stuck to my mind, so I'll give it to you guys and maybe mislead you. But okay, so if I think about these boundary algebras as being, von Neumann algebras as being associated to diamonds, then let me think about M as being some Rindler region, for example, just for simplicity. So here is this Rindler region here. Oops. Use highlighter. Here is this Rindler region. And then in beta, this particular subalgebra is just a subalgebra. It's not really a subalgebra in that it's sort of localized in some other region like this. In fact, it's really not, and that's why this is misleading. It's really some subalgebra of operators in here somewhere. And maybe I should sort of draw some thinned out version of the algebra or something. But to be precise, I'm just going to draw a subalgebra as some kind of diamond like this. But just be warned, this is a little misleading. Now, okay, good. That's the starting point. But we also have the complement region, right? So the complement region M prime, we had some algebra on the complement region, which you get by applying beta prime to n prime. Okay, remember beta prime is some different map that you get from this other DHW condition. But if you apply that to n prime, then you get some other algebra, which is now a subalgebra on the left here. Okay, and so the conditional expectation takes you from m to n prime, and then there's some primed conditional expectation, which takes you the other way. Now, one interesting thing that you can show is that I can rewrite this algebra. I can think about the commutant of n prime beta. So the commutant in this picture is just everything inside this diamond here. So it's something that contained in it is m and n beta. But you can rewrite that as m, all of the operators generated by m. So this little symbol here means take all operators in the algebra and take products and sums between these two algebras here, where E is just the projection to the code subspace. So it's a single operator. So if I take that single operator and I include it in the algebra of M, then I get this commutant algebra. Okay, and that might not mean too much to you, but this actually has a name, this M1, M union E, or M, the algebra generated between M and E. It's called the Jones extension and plays a central role in the discussion of index theory for subfactors. Okay, so you also might not know what that is, but that's where the Jones polynomial, so-called Jones polynomial, was first discovered. Studying type 2 von Neumann algebras and their possible subalgebras. And in particular, there was a conditional expectation, and this Jones extension sort of plays a role where you essentially do this many, many times. So you get a bunch of these extended algebras, and that allows you to try to classify something called the index, where the index is some measure of how big the subalgebra is inside the other algebra. It's some number which tells you, roughly speaking, how many times the subalgebra fits inside the bigger algebra. Okay, so that's one example. But it's interesting to me that this Jones extension is exactly related to this complementary recovery condition. So this complementary region, the commutant of it is the Jones extension. Another thing that I'll give a picture of, from this picture, is something called the relative commutant, which also plays a central role. The relative commutant is the commutant of n beta, but inside M. So it's everything that commutes with n beta, but that lives inside M. So it's this little region here, if you like. And if you go back to the original example I gave of a conditional expectation, it's just bounded operators on HC, the thing that we traced over. That's what this relative commutant is. Okay, good. So the things that I gave above, this quality of relative entropy and the quality of bulk and boundary modular flow, I discussed them in the paper. You can go in more detail. But the one thing that I want to go through a little bit more is how you see this Ryu-Takanagi area operator coming out, which was sort of a big deal was made of by Harlow and others. When you have this entanglement wedge reconstruction like a structure of this complementary recovery condition, then you naturally just get something that looks like the RT formula, the Ryu-Takanagi area formula. So the idea is that naturally associated to E is the following structure. So you can show if you have an E like this, then M is roughly a tensor product between the subalgebra n beta and this relative commutant. Okay, so that this might seem trivial or something that you can always do this, but actually no. When you're talking about von Neumann algebras, it's really not it's not always the case that you have a tensor product structure. Right now, this requires some extra assumptions. Actually, it requires that the algebras are factors and that there's some normalcy condition, which I'm not going to go into. But essentially, this is true in general. So essentially, some version of this is true for general von Neumann algebras. If you have a conditional expectation, you have this tensor product structure. And more importantly, you have this tensor product structure and the states that are fixed by the conditional expectation, which remember for us was the state in the code subspace, are factorized. They're always factorized between this relative commutant and the subalgebra. Is there a question? I heard some noise. So if we have this tensor product structure, then it's easy to see that the entropy, just the entropy associated to M for such states that are fixed by the conditional expectation is just additive. So you get a sum between entropy on the relative commutant and entropy on the subalgebra. Okay. This entropy on the subalgebra is going to just become the bulk entropy. So for states on the code subspace, you can show that this is just the bulk entropy. So it's the entropy in the bulk region. Now let's unpackage this other term, which is this entropy on the relative commutant. So to understand that, let's think about the state on the relative commutant. So that means I'm going to take my state, which is on the code subspace, or fixed by the conditional expectation, and I'm going to compute expectation values of operators in the commutant. But because it's fixed by E, I can just for free put in E. And then there's an interesting fact about applying E to the relative commutant. If I apply E to this NC, then by definition, it's in N beta. Just by the definition of the conditional expectation, it always maps to N beta. But then if I consider the following equation, if I apply N beta on the here, I can put it inside the conditional expectation just by using this bimodule property. But because NC commutes with N beta, it's the relative commutant, commutes with N beta, I can commute N beta through here, commutes through here, and then I can pull it out using the bimodule property. So at the end of the day, you see that N beta commutes with E. So indeed, E applied to the relative commutant is in N beta, but it's also in the commutant. So that means it's in the center of the algebra. So it's in the center. So that means that if I apply E to NC, oh well, let me change my pen. Oh, what happened? Oh no. Sorry guys. wasn't thinking. Are we back? Can you see my iPad?
Yep, we can see
Yeah,
it.
we're back.
Let me charge with my phone. Okay, so what am I saying? So E applied to the relative commutant is something in the center. So that means if there was a non-trivial center, so it might be a factor, in which case the center is just the identity, but there can be a non-trivial center. Then we can just decompose E as a sum over projectors onto the center and times some just numbers. But these numbers depend on what we put in, this relative commutant, NC, the operator in the relative commutant. And in fact, you can show that those numbers are really a state. So their state is linear functional from the relative commutant to numbers, the complex numbers. So, so here, good. So if we apply E here, we get a sum over the central projectors times gamma, which are the states. But these states, it's important to emphasize, just depend on the conditional expectation. They don't depend on the state that we're interested in the code subspace. They're state independent in that sense. They just depend on a given conditional expectation. But then you plug this form into the entropy on the relative commutant, and you find that it just becomes the expectation value in the state of interest of these central projectors times some entropy of this state gamma, of these states gamma. And this is exactly what you would call the area operator. So it's the expectation value of some operator which lives in the center, and the coefficients of that operator are these entropies on the relative commutant. Okay, and then again, you have the bulk entropy term. So this looks like the area term, and this looks like the bulk entropy term. And it's just a consequence of this conditional expectation. Okay, so yeah, so this was extensively discussed by Harlow. So one thing I should say is that because these entropies that I'm talking about are all finite, I'm really talking in this so-called type 1 setting where you have finite entropies, but really for quantum field theory, we have type 3, which means our entropies are infinite. That means that this discussion doesn't really hold, but there's still a version of this discussion where you don't talk about entropies, but you can still define this area operator. So I think that's interesting. I don't know exactly what to make of that, but you know, at least there's something you can define. Good. There's an interesting way to write this, which makes it a little bit more like the RT formula, where you write it as some kind of minimization. So you can prove the following result. You can prove that the entropy, good. So we're trying to calculate the entropy of the boundary region M for some state on the code subspace. You can always show that that's less than the following quantity, the following sort of minimization quantity. So I minimize over all possible reconstructible algebras N. So remember, to prove all of the results above, we needed something called C reconstructibility. We needed complementary reconstructibility. Here, if I just look at a reconstructible algebra, which, as I mentioned before, was any subalgebra, then you can show that the following sum of entropies, just the bulk entropy here, plus now the entropy on the relative commutant, is always bigger than the entropy that you're interested in. So if you sort of minimize over that, then if you actually find equality, you can prove that it's only achieved if and only if the N that you're working with is C reconstructible from M. So if you find the entanglement wedge. So you take N, which is some subalgebra of the entanglement wedge, you minimize until you get all the way to the RT surface, and then you find complementary reconstructibility. So this looks a little bit like the RT formula. It's suggestive, at least. However, there's some issues. So I'm going to point out those issues. The first is that it's sort of not correct in some sense, because I mean it's correct, it's a theorem, it's just not correct in ADS-CFT. So if I take any subalgebra of the entanglement wedge, say some geometric subalgebra, then it doesn't always have a larger generalized entropy. Oh, sorry, I should have mentioned that this formula looks like a generalized entropy because it's a bulk entropy term plus some other term. Okay, and let me think of that other term as the area operator. So good. So not all subalgebras in entanglement wedge have a larger generalized entropy. For example, the generalized entropy always decreases along the entanglement wedge horizon. So if I just move in the null direction away from the RT surface, then just by focusing, quantum focusing, then actually the generalized entropy has to decrease. That's one issue. The other issue is that the area operator that I just mentioned is not really an area operator. It's some state-dependent entropy term. You can actually fix this issue by talking about a special class of codes where your states, these gammas that I referred to, are all maximally mixed. Then this issue goes away. Perhaps the biggest issue is the following statement. If I manage to do this minimization and I achieve a minimum for one state which is sufficiently entangled, then I can show that it achieves the minimum for all states. Okay. So this is also not something we really expect for the RT formula. For some states, the RT surface will move around. This is something I'll never be able to fix with the exact recovery. So this, you have to really move beyond exact recovery. Okay. So let me. How much time do I have?
We're fairly flexible, so
okay. So
I think
keep
Moshe
going
has
until
to
everyone
teach
gets
at,
bored.
yeah.
Okay.
So
Okay.
Moshe has to teach at 2, so he'll have to leave 10 or 15 minutes before.
Okay. Oh, 2. Okay. Oh, that's a long time. Okay. Well, I probably won't go that long. Okay. So now I'm going to move on to the more speculative part, although I've already given you some speculations. Now I'm going to sort of try to see how far I can push this, still assuming exact recovery. So now the interesting thing to do is to think about multiple boundary regions. Right now I just had M with some fixed boundary region. So I'm going to talk about multiple boundary regions or boundary algebras, M1, M2. And the first thing I'm going to prove is something called entanglement wedge nesting. So it's stated as an exact theorem in this language. So it states the following: if N1 is reconstructible or C reconstructible, you only need reconstructible, so that we remove that. If N1 is reconstructible from M1 and N2 prime is reconstructible from M2 prime, then if M1 is contained in M2, then the theorem states that N1 has to be contained in N2. Okay, so let's unpackage that with a picture. So the main assumption is that M1 is contained in M2. So what does that mean? Well, if I take the commutant of M2, then it means that M1 commutes with M2 prime. Okay, so if I have some containment like this and I flip it like this, then I'll get a commutant algebra that commutes. So let me draw M1 here and M2 prime over here, and they're space-like separated because they commute by assumption. Then in the bulk, we know that there's some RT surface and RT surface 2 and some RT surface 1. Okay, and those are the entanglement wedges. And then reconstructible algebras are just any subalgebras of that. So N2 prime, for example, is inside here, and N1 is inside here. So you see from this picture, at least, the expectation in ADS-CFT is that indeed N1 should commute with N2 prime, which then implies that N1 is contained in N2, which is what we wanted to prove. And in fact, okay, so I'm not going to go through the proof, I think. Yeah, I'm not. You can prove it just based on the properties of these quantum channels. You can prove this statement. Okay. So a corollary to this statement is that if I picked M1 equal to M2 equal to M, then the entanglement wedge nesting theorem um, just tells you this assumption that I've been making, that all subalgebras of the entanglement wedge, a reconstructible algebra, are C reconstructible algebras are reconstructible. So this is the thing that proves that statement that I've just been telling you. Okay. The second result is the following. So it's the consistency of this conditional expectation. So if I have M1 is contained in M2, and they're both C reconstructible algebras, there are two C reconstructible bulk algebras, N1 contained in N2, then the conditional expectation that you get from this is consistent under restriction. That means that if I consider the larger algebra, there's a conditional expectation from that to this subalgebra N2 beta, and I restrict that to the smaller algebra M1, then it's equal to the conditional expectation about E1, which then maps to N1 beta. So this is a non-trivial condition on all of these sort of conditional expectations that you would get from boundary algebras. And it's this condition that actually proves that this complementary recovery condition from these boundary algebras is exactly the same as the structure that you find for superselection sectors. So there's some superselection sectors are just some way of studying sort of global charges in quantum field theory in an algebraic quantum field theory language. And it has some consequence for the operator algebras. In particular, you have some operator algebra associated to all charged operators, all operators that you can imagine, but then you'll have a subalgebra of neutral operators. And that subalgebra comes with it a conditional expectation, and this conditional expectation is usually assumed to be consistent under restriction. And that's just because that makes sense if you think about projecting to the neutral algebra. But here it just pops out of this complementary recovery condition. It means that the mathematical structure behind superselection sectors, which was essentially formalized in this paper, so they formalized this mathematical structure and moved beyond just symmetry. So it was just a formal structure that didn't need some symmetry or some global symmetry. But the important ingredient in it was a conditional expectation which had this property. And so this sort of strengthens, I think, a connection pointed out by this paper that I mentioned earlier, where they sort of speculated about the connection between this sort of superselection sector structure and ADF-CFT. Okay, the next thing is there's an important issue. And this issue goes back to a paper by Kelly from a while back. If you take the following, if I have two boundary algebras M1, M2 that overlap, and they overlap on a fairly extended region, okay, fine. It's not tiny or anything. It's just a fairly extended region. And I assume that I have C reconstructibility for both of these boundary algebras from some bulk algebra that I'm sort of drawing here. The associated bulk algebra, here's one and here's two. Then you can show that is based on some assumptions about the existence of some state that's cyclic and separating for this intersection algebra. So this algebra here. So that means there's a sufficiently entangled state in that intersection algebra that's on the code. And this is totally not an extreme assumption at all, because the vacuum state would have that property. Then you can show that the bulk algebra N1 union N2, or the things generated by N1 and N2, is C reconstructible from M1, M2. That means that the bulk algebra associated to M1, the union of M1 and M2, is this region. Okay. At least if this picture was to make sense, would be as a consistent story. And indeed, we know that that's not true, because we know that it's this region, right? So this property is called additivity. So it means that the bulk algebra associated to the boundary algebra is additive. So, so the additivity is related to this sort of taking two algebras and generating everything from it, from the two. So as I said, we know that this is not true in ADS-CFT. So it used in a central way this cyclicity on this intersection. I don't want to remove that assumption. I'm not advocating that. And Kelly was also not advocating that. The resolution is really you have to go to this approximate recovery. What happens there is that you still have cyclicity. You still have that statement, but it just loses its power. You can't prove statements as easily without it. Okay, let me make some final sort of obligatory comments about entanglement wedge phase transitions. This is really pushing the boundaries of what I can say, but I should at least try. So I'm going to think about the case where we have two boundary algebras M1, M2 that are disjoint from each other. It's well known that as I vary M1 and M2, you get a phase transition in the entanglement wedge, right? So if they're very far from each other, the entanglement wedge is just sort of the union of these two regions here. But as it grows, then you get a non-trivial sort of connected entanglement wedge over here. And the pictures I'm drawing are for sort of a 2D CFT, and that's really the case that I'm going to think about now. And in that case, you know, this is a phase transition that happens when the cross ratio of the boundary points, which is just some number, goes between 0 and 1, has a phase transition at 1/2. So if I focus on this two-dimensional CFT case, then a nice property of that is that if I take the complement of these two intervals, then I get two intervals again. So this is also two intervals. This is two intervals. So if I continue to assume reconstructibility for these two separate algebras, N1 and N2, so M1 and M2, so I have some region N1, N2 associated to those, then that's fine. But then the question is, what is the reconstructible algebra associated to the algebra generated by M1 and M2? So I'll call that N12, and the question is, what should I pick for N12? And holography suggests that there's only two options. N12 could either be additive, as in it's just locally generated by N1 and N2. That's this picture over here. Or the complement could be additive. So N3, 4, if I think about the algebra generated by N3, N4, and I take the commutant of that, well, the picture of that in the bulk is really, so this is N3, N4. The commutant is this region here, which is exactly the entanglement wedge in the second case over here. So that's the entanglement wedge there. Okay, so it's either additive for 1, 2, or it's additive for 3, 4. So I gave this a name called a dual additive. So it's just an assumption that those are the only two possible reconstructible algebras. And I think this is sort of analogous to, it's an extra assumption you have to add to study holographic theories. And it's sort of analogous to this extended Cardi regime, which is a well-known feature of holographic CFTs, and really explains, you know, the Hawking-Page phase transition, where you sort of have two different phases. And those two different phases are just analogous to these two options that I've advocated here. So what is controlling which algebra is reconstructible? Well, you can actually prove a quantum minimality condition based on this, on the assumptions that I have, where you have two options. You just compute the entropy of N1 union N2, and then you include area operators that are sort of additive on the two regions, or you compute the sort of the complement version of that. And you use the split property, which I'm not going to go into, to show that the area operators add like that. Oh, okay. And the statement is that SM for some, so this is M1, M2, sorry. this is equal to this minimum, and whichever one wins, whichever one is the minimum, then it's that algebra that's reconstructible. Okay. Yeah, I wanted to, yeah, I'm going to skip this point. So I tried to study this code in a sort of funny way, and I'm not totally sure what to make of it, but it's the following idea. So you can try to study this code by introducing another code subspace. So you have a code subspace, the original code subspace that we introduced. You can introduce this other code subspace called the split code, which comes from the split property. So I'm not going to explain how you get it, but there's another code subspace that has the property that n12 is always locally generated by n1 and n2. So that means you sort of have two different code subspaces where you have two different reconstructible wedges. And I'd like to think of this as some kind of analog of what happens in the Hawking phase transition, where you go from sort of the thermal state in ADS, which you can think of as sort of an entangled state, a pure entangled state between two copies of ADS, and then sort of the black hole phase, which you can think of as a sort of a thermophile double above the Hawking phase transition. And so you can, in principle, you can think of these as two different code subspaces, and there should be some small overlap between these two. And in fact, you know, there's papers that have proven that there is a small overlap between these two. And in the version that I developed, because we have exact recovery, these code subspaces are provably orthogonal. But the idea is that really, when you go beyond exact recovery, then they won't be orthogonal, and you'll be able to somehow go from one to the other. But this is a little speculative. Okay, so let me finish, and then I'll ask questions. Yeah, so really the only comment that I have to finish is that, you know, the future work requires to understand beyond exact recovery. There's a whole bunch of interesting things that happen. You have Alphabet Story by Hayden Pennington. There's an interesting story about breakdown of complementary recovery, a very recent paper on that as well. And yeah, so let me finish there. Ask for questions.
So I have kind of a general question that I wanted to understand. So I guess somehow in here with ADS CFT, you have this n parameter, and I think many things like the strict code subspace, it seems to me that they're precisely defined in some large n limit, and then if I make n finite,
yeah,
maybe they're not so precisely defined. So I guess that's sort of the question. You know, how many of these things kind of rely on some strict large n limit, and what happens if we make n finite?
Yeah, so I don't know. I'd like to say that's this distinction between exact.
Is that the exact. Okay? Yeah, I was going to ask that.
But in some sense, I think, you know, for many things, the strict n infinity limit doesn't really make sense. So that's what we're seeing here. We need n to be finite.
Right. Something like the Hawking phase transition doesn't make sense.
Exactly. Like if you think about the microcanonical ensemble, or there's all sorts of things that you have to go beyond that. And I think I'm limited by that. N hasn't played, you know, I don't know what n is. Like I haven't told you what n is. But I think that will come in when you think about non-exact recovery. That'll be an important aspect of that. Sort of.
I see. Yeah, it feels like it should play an important role somehow, but I'm a bit confused about how.
Yeah, no,
I guess even with Carlo's finite dimensional things, there were many things that were exactly true there, and maybe I wouldn't expect them to be exactly true even for finite and ADS CFT. So it's a little bit.
Well,
confusing.
Yeah, right. Yeah, that's right. Yeah, I mean, you know, this is really, for me, this is just the first pass. I sort of hope that some of this structure survives. I think there's a whole mathematical literature out there studying super selection sectors, and this kind of code where they have assumed, in some sense, assumed exact recovery, and then it would be nice to break that a little bit.
Mm-hmm.
And maybe that's really what ADS-CFT is,
Mm-hmm.
as a bold conjecture.
Question related to the discussion of the earlier stuff of Kelly. Do these maps glue more nicely than like the density matrices themselves, or do they have sort of nice consistent gluing conditions?
You mean
if I have like the conditional expectation on region AB and BC and they glue on the overlap, do I automatically get something on ABC?
They glue on the overlap.
They agree on the overlap.
I think that's exactly what
together.
this is. I think this is exactly what this is. So yes, but only because of the cyclicity statement. But yeah, they do. There's a consistent. Yeah, you can prove in this case with exact recovery that there is a conditional expectation on the bigger thing, given that it exists on the smaller ones, and there's some property on the overlap. They're consistent on the overlap by this restriction condition, which is this other 2 thing. So they're always consistent on the overlap for that region, for that reason.
So in some way, you can kind of build like a sheaf of these on them.
Yeah,
on the boundary.
Right. So there's this whole story of super selection sectors, as you imagine, and indeed, there's it becomes very mathematical and beyond me at this point. But yeah, it's indeed it's something like that. You have these subalgebras that somehow sew together in some nice way, and
The density matrices don't sew together nicely, and so it seems it's sort of some nicer way of that. The theory becomes more local, and you can patch it together in the way that density matrices don't.
Yeah, that's right. So there's this whole technique for that, and category theory is very important for that. So yeah.
Okay.
Maybe just one more question. So, and you might have already said this. So, but anyway, some of these results, I guess, were understood, say, in finite dimensions, and then there are infinite dimensional results. But then in infinite dimensions, you have these different types of algebras, and I guess maybe just summarize what's sort of the status of getting from finite dimensions all the way to the actual type 3 whatever algebras that we think are the right ones.
In terms of this structure, then it's done.
Okay, so are there some aspects of this that, or of this general quantum error correction story that or entanglement recovery that we don't quite know the right language for the type 3 phenomenologies, or it's kind of understood at this point?
I don't know. Everything is uncertain because of this non-exact recovery. So
yeah, okay.
I'm not really sure. So for example, you might ask, is there a center? It seems like a really simple question, and Harlow and company made a big deal about that being quite important for the area operator.
Right.
And I'm sort of in this uncertain times where I'm not sure whether that's true. So in the paper, I wrote it including a center just because I'm not sure. But you can prove, for example, that the boundary algebras of reasonable quantum field theories are definitely don't have a center.
Okay.
So then the question is, does the bulk one have a center? And I actually know there's pretty good reasons to believe that maybe it doesn't. In which case, then really understanding how the area operator is a local thing becomes a very important question. Yeah, I don't know.
Okay.
Yeah.
Thank you.
Mhm.
Okay, perhaps we should thank Tom again then.
Thanks for having me.